advanced methods of synthesis of nanomaterials. It's not very comprehensive. I have tried to classify. You can see their physical versus chemical methods, bottom up versus top down, soft versus hard methods. So these are considered extremes. If you're doing bottom up, typically you would start with a solution where you have the ingredient in the form of an ion, for example, right? And then you neutralize or you change the oxidation state, you ligate it differently, and then make the system grow. So you may have a control on the nuclearity, the morphology, the shape. So this forms the chemical part, the bottom-up part. These are interchangeable words, by the way. On the other hand, you have the top-down or the physical methods where you have the bulk chunk, and you want to fragment it, and you want to chop it such that you are able to produce very fine particulates, very fine features. So these are all top-down or physical methods. Chemical methods, going by the description what I just said, they are also relatively soft methods, softer methods, so to say, in comparison to harder methods, physical methods, which involve sometimes enormous energy density. So we will take a glimpse of all these different methods which have been used in the last years and in the last 2 decades, and how they have been developed to produce well-defined nanomaterials with a possibility for upscaling for industry. So many times we talk about hybrid methods where you tend to combine in some process steps hard method, physical methods with chemical methods, eventually with the goal of achieving the given nanomaterial. So this is all about terminology. We'll get a bit deeper with starting with the physical method. As I said, physical method is typically energy intensive because you want to take the starting material in the form of a material in bulk, and you want to fragment it or you want to evaporate it, form the same material in the vapor phase. If you talk this language with respect to some ceramic or metal, you can imagine the kind of energy input required, temperatures required, right? It's not some simple vaporizable organic entity. If you want to vaporize, for example, tungsten, you can imagine what kind of energy is required as input. So is the case with many interesting oxide materials. So essentially you vaporize the material starting with the bulk form. Typically they are called targets, and you impinge energy in the form of laser, electron beam or whatever, vaporize it. Then there is an important concept called entrainment. If you simply have this vapor go around and deposit by itself, you will end up with some sort of nanomaterial, but you may not like it, you may not have the control over it, the kind of particle size you want, the texture you want, the dimensionality you want, you may not have control. So there's a lot of game in this entrainment. I can tell you there are at least 2 to 3 Nobel Prizes sitting there in that entrainment. People learned how to control vaporized material and nucleate interesting nanomaterial species, new species. Then you derive the given nanomaterial. So when we talk of the system which comes out in the form of a nanomaterial, it could be simple 2-dimensional films, 2 clusters, flying clusters, free flying clusters. You can also make nanotubes, nanorods of variety of materials. So there's a lot of play here in terms of entrainment. And I'll tell you how literature has approached, people worldwide have approached this aspect of entrainment and achieved a great control on nanomaterial production using physical methods. Some commonly known techniques I have listed out here. There are specialty ones down there. There are other resource people who will focus perhaps on those specialty methods. I am bringing out broadly laser ablation technique, arc discharge, and ball milling. Ball milling is, so to say, poor man's method. You have hard balls. I think it's made up of tungsten carbide or something. And you feed in the vessel, powder with larger particle size, typically few hundred microns or whatever. And then keep the vessel spinning, shaking vigorously such that there's a lot of collision. And in the meanwhile, the powder gets crushed. You end up with much finer particular size. This has been in use even before the so-called nanotech revolution. And people know the results. In each system, it needs some optimization. And you finally end up with fine powder of a given material. But what you are missing is greater control in terms of the particle size and the distribution. So ball milling has limited application, only for some applications. If I want to produce a metal cluster with exactly 5 nanometer diameter or something which is containing 100 atoms each, ball milling is certainly very, very far away from it. You cannot be using it at all. It is mostly a method with high throughput, grass applications where you don't seriously depend on the particle size. Okay? But it is being used. In comparison to ball milling, arc discharge is a method where a lot of new materials have come out. So I'm going to spend some time on it. And laser ablation is even more sophisticated technique where you have very precise control, even in terms of, I told you, 100 atom cluster, 101 atom cluster. I can have control on with such precision. So I'm going to spend time on arc discharge to some extent, and I'll move on to laser ablation. Arc, as you all know, we all have seen arc commonly in cinema projection, right? 2 carbon rods in between the strike arc, and then it starts glowing and bright light comes out, and that was being used for cinema projection. But it's nowadays, I think, more different techniques are available. That's essentially the arc I'm talking about, but this carbon is not being burnt using arc, not in air. This is in controlled atmosphere. It is typically few millitorr kind of vacuum, and in an enclosure where you have helium, typically helium inside, some inert gas inside. You don't want the carbon to burn. You want it to just vaporize in the arc, and then you want it to come out as some sort of carbon nanomaterial. What is that? God knows. Now the question of process optimization. The pressure can have an effect on the arc, the inert gas, the atmospheric pressure, the kind of voltage you apply, whether DC, AC, the magnitude, the spacing between the electrodes, the diameter, all sorts of things get in. Purity of carbon, right? If you want to prepare impure carbon nanomaterials, then you have a chance. You can actually dope or insert, physically just insert, make a groove and insert some sort of oxide there, then that also becomes part of the nanomaterial. So what I mean to say is, in this very high energy process, you are talking of temperatures which are typically 3000 degrees centigrade or so. You are essentially deriving white light out of it, right? And under those conditions, carbon is simply vaporizing. And what is your entrainment? Oh, just the vessel here, filled with fractional pressure of helium. That's all. Again, poor man's technique. And as the carbon vapor comes across the helium atoms around, helium gas around, it tends to cool down and nucleate into particles and, sheets, cage molecules, tubes and whatnot. Usually if you're using DC, one electrode gets consumed and the other keeps growing. This is what also people see. Typically carbon material tends to grow, deposit on the other electrode. Or sometimes it deposits on the surface of the vessel as well, which is taken out after releasing the vacuum under cold conditions, normal room temperature condition. You just wipe off all the carbon material which is deposited and it will be very rich. It will contain fullerenes, contain tubes, soot, a lot of soot, and maybe some graphene as well, I don't know, right? And even carbon balls, spheres, not cage molecules, just balls, hard balls. Some onion structures maybe too around there. So arc produces a lot of carbon nanostructures. Is quite a good throughput method, and with control on the production, people have even made it into a process to produce carbon nanotubes for industry. Very successful batch process. Single wall carbon nanotubes, multi wall carbon nanotubes, enhancing the yield of these tubes in the carbon deposit. But it's never going to be 100% nanotube, okay? It needs a lot of processes with respect to purification, which I'm not paying attention at all. Fractionation, purification, burning out the unwanted, all that is required before you actually get it out as an industry product. But this has already been in use, and that's how people are selling gram and kilogram quantities of carbon nanotubes, single walled and multi walled. Let's leave the arc discharge there and move on to laser ablation, which is even more interesting. Of course, the instrumentation required here is quite expansive. You need a laser which can shoot out pulses, photon flux, very high energy density. Typically one uses Nd:YAG, for example, or excimer laser. With Nd:YAG you are relying on the 1064 IR photons or the frequency doubled 532. And then the laser is focused onto a target here, and target is the one which is giving out the vaporized material. The target can be anything. Target is a material from which you want to derive a nanomaterial, right? So it could be a piece of metal, it could be graphite, pellet, it could be an oxide pellet, anything, even polymers. Now, as the laser is focused, you can see the kind of energy density one would achieve there, and you will have the lot of different species coming out. These will be ions, clusters of ions, right? And big chunks. Simply bigger particle also may get chopped off with the laser. And as they fly out, you can keep a substrate and collect the material. That can become a film actually. Good thing about laser is it just doesn't care what material it is evaporating. It can be hard tungsten, it can also be a gentle polymer, organic substance. It doesn't care at all. Basically you need to play with the laser fluence in order to not to do certain things. If you're working with tungsten kind of refractive metals and materials, some oxides, then you need to increase the laser fluence. But if you are working with gentler materials, probably you need much less fluence. What is interesting about laser is, as it doesn't care what it is evaporating, it can evaporate everything, and it can maintain the composition of what is being evaporated even in the plume which is coming out here. This is plume, and it will have the plume deposited on the substrate. So you are able to convert the target material of whatever complicated stoichiometry into a film of the same stoichiometry. That's the beauty. So you have derived a 2D nanomaterial there of the same stoichiometry. Where it becomes important? If I'm preparing, for example, tin doped indium oxide, ITO films, right? FTO films. How sensitively the properties vary if I vary the doping content, the fluorine content, right, in tin oxide, or tin content in indium oxide. Tremendous variations will be there, but you need to have a fine control. And if I am preparing, for example, YBA2CU3O7, not 7, 6 minus delta, the delta could be 0.1 or 0.12. How do I do? Laser. If I use laser ablation, it will just take the whatever your pellet composition is, right? It just goes and dumps it in the form of film on the target. And that's why laser ablation for films has become so popular, and there are commercial systems available to do large area laser ablated films. Let us move on. What other nanomaterials can be produced using laser ablation? Remember, when you are shining laser on a given material, you are essentially chipping off where the laser is getting focused, right? And the moment you chip off, you can imagine that charge is also